Okay, we're live. All right. So. Okay, what's up, y'all? We're doing some problems from a worksheet, and let me pop this chat out just in case. Pop out chat. Send you over there, and let me send this link. All right, boom. Yeah, log functions are just one of those things that everybody has a problem with. What is this? Okay. What were we going to do? Are you here? Okay, I will be right there. Are you trying to get me to park the car? Because I'm on live stream right now. Okay. Okay, so average watch time. Somebody's here. Who's here? Say hi in the chat. Okay. Logarithmic functions. All right, so we have our first function in CRITA. We do not. All right, so here we go. Clear these tabs. Some of those are not even from this worksheet, and import this image, which is that one. So this is number one from our worksheet that we're working on today. Let's expand this a little bit. Okay, so determine the domain of the function log of 9 minus x squared. So we learned a lot of these transformations in pre-calc, and I think those tend to be really useful. Let's try to think through this thing one step at a time. So our base log function is that. Wow. Okay, so our base log function would look like, if you forget this, just remember the exponential function is kind of like so. Right? That's terrible. That's going to be good enough. And then you can reflect that. That's not good enough. We're going to make it like that. Then you can reflect that over the line y equals x, which this should be above it, but you get the idea. And you would get another function, which looks like got this asymptotic behavior here, and then something like that, right? So they should reflect over y equals x, but I can't draw, so they don't. Anyway, this is our log function. That's pretty good. Nice job, me. And we want to do transformations on that to make this thing. Now, this is going to be slightly different because we don't have a linear function in our argument. That's actually a quadratic. There's no negatives here. Or no, there are negatives. This is the equation. This is the quadratic 9 minus x squared. So let's just think about that, what that thing would do for a second. If we put it in standard form, it's negative x squared plus 9. Now our leading coefficient here is negative. That means it's concave down. So if we had our thing, it would look something like this. The only question is, where's the y-intercept? And it's here. If you plug in 0 for x, you would get y equals 9. So this is 9, then it goes like that, and at negative 3 and 3, you have your roots. You all remember this from Algebra 2. If you do not remember this from Algebra 2, hit it in the chat. So anyway, we have to think about our log function and the domain of our log function. It's really important that you think of the domain of your log function, okay? But the things that can go into this function and come out of that function are going to be the things that go into the log function. So we just have to think about what can exist there. Now, the log of x, if you look at our base log function here, we only have values where x is positive. Can't even be 0, okay? So only the values that come out of this function, which are greater than 0, can go into f, the function that we're working with here. Okay, so let me get some of this nested stuff. Okay, so x here, this isn't what they're asking, but let's just think about it. X can be between, x is on the interval, it's an element of the interval, from 0, or rather, -3 to 3, okay? We can't have it be equal to -3 and 3, because if we did that, 9 minus -3 squared equals 0, and you can't have the log of 0. It's not defined there, okay? The same thing for positive 3. So that's the domain of our x, all right? Okay, so then we have to think about what the natural log of these numbers would be. And so let's think about the values that we're going to get out on the y. So these y values are going to go into this function. And everything is greater than 0, so you're going to get -infinity up to the log of 9, essentially. Yeah, so yeah, that's our outputs. Y is on the interval from -infinity to the log of 9. And this is just a number. You can put that in your calculator and get a decimal, but that's the exact value. That's terrible explaining. So hopefully that doesn't make anybody quit the live stream. It's just kind of the process. So let me try to give a synopsis of what I just did. I see that I have as my function f here the natural log of 9 minus x squared. I understand that whatever is inside here is going to be the first restrictions on my domain. This doesn't give me any restrictions on my domain for 9 minus x squared. 9 minus x squared has, let's say if we have another function g of x. For this function, x can be any real number, and y would be -infinity to positive 9, because it's that concave down parabola. Okay. So the y's that can come out of this function will be the inputs to this function. And I hope that makes sense. That's, it's pretty straightforward after you've been doing it for a decade, but the first time you hear this, it's a little confusing. So then we have to think about, of those possibilities, the numbers between -infinity and 9 that can come out of this function and go into this function, which ones are allowed to be put in there? Oh no, we actually do want the domain. Yeah, we want the domain. Sorry, I interpreted range from that. And those numbers are the numbers that are positive, has to be positive. So we can only put y's into this log function which are positive. That's y has to be, and we're talking about y specifically from g of x, has to be on the interval from 0 to 9 then. So we're not going to take this entire interval, we're going to break it off to a subset. So now let's work backwards. What x's go into g and cause numbers to come out, which are between 0 and 9? That's going to be numbers between the roots here, -3 and 3. And just really comfortable solving this inequality. Okay, -3 and 3 will give that. All right, I'm just going to keep moving since no one's in the live stream, I think. Actually, let me just look. 2 playbacks. Whoa, I have a concurrent viewer. A single concurrent viewer. Concurrent viewer, please say hello in the chat so I know you're here. Otherwise, it's that stealth watcher. It's the person who always watch, never comments. Uncle Sam will come in the chat. Okay, next question. So we did 2 in another video. I'll run 2 again for anybody who hate me. That's my favorite math student. I'll run number 2 again since I kind of like uploaded it. It's probably still potato quality. The live stream comes out immediately better. And boom. And B. But just if there's any like confusion on any of these things that I'm saying, especially on that domain range one, and just to be clear, the last one, the domain was -3, 2, 3 for F. This was the answer to the last one. The reason why you can't include the -3s is because the output is like 0 from 9 minus x squared, and log doesn't have 0 in its domain. So that's the answer for problem 1. And I'll run problem 2 unless, okay, great. Unless you don't want me to, so I'll just do this really quickly. If anyone needs it, just go back to the other video which I posted right before this. Okay, so we want to cancel log base 3 to get this out of our argument here. The way I do that is I raise each side to the power of, into the exponent of 3 as the base, if that makes sense. So we get log base 3, x plus 1 equals 3 to the log 5. And these cancel now because those are inverse functions. When you compose inverses, the argument pops out. And then we subtract 1 from both sides, and we get 3 log of 5 minus 1. Now, I'm saying the steps that I do, but I don't write them, right? This is all like, this implies this, implies this, implies this, and, you know, proficient, like somebody who can read math will understand what this is, so your teacher should understand this. You don't need to be like, -1. That's algebra and stuff. Okay. Any questions on this? And this is an exact value. You can put this into your calculator. I think it's like 4 something, or maybe 3 something. But it's super not important what that is. Okay. So now we're going to go to number 3. And I'm moving fast, so just pump the brakes if you need me to go back on anything. We want to do number 3. Okay. Great quality. All right, the next one will be potato quality. Okay, solve for x, so same sort of thing. All right, so here's another log function. Let's not use red, let's go king color. X to the 1 plus log of x. Now, you're going to see this a lot where you get log x. This makes you feel like this is log times x. That's not a thing. This is log of x. We should be really careful and use parentheses so that we're preserving that function notation. But for whatever reason, we don't. Now, we're going to use a log trick here. They call this a log rule, but I just call it a trick. I'm going to take the log of both sides. So I always do the natural log for this because it doesn't matter what base. So I'm going to take the log of the whole left side equals the log of the whole right side. Okay. Now this gives me access to that power rule. I can bring this down as the coefficient out front. When I do that, it's really important that I put that in parentheses. So I want this whole thing. That's what had been in the exponent. Now it's going to be times log of just the base, x. And this is equal to log of 100. This is still a constant number. It's just log of 100, whatever that is. Boom, 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 boom. So, let's see. What are we going to do? Let's distribute this. Oh, you know what I'm going to do? I'm not going to use the natural log. So I'm going to change this to be the same base as the log that they gave. If they don't write the base on the log, it's log raised 10. So I'm going to do this. Okay, there we go. So then that's going to come down, and we've got 1 plus log x times log x equals log 100. Okay, so now we'll distribute this, I guess. Log x plus log. So this is log of x squared, right? Yeah. Oh, this was actually tougher than I thought. Think about this. Boom, 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 boom. There must be like a sum rule here. Oh, I know what we can do. Yeah, I feel like this is would that work?
It's fine. It's just Emma on the thing.
Well, it's not just Emma, but she doesn't care for numbers. That's actually really tricky. Oh, what are we solving for? X. What rule goes here? Because it's not log of x squared. Yeah, this is a really good problem. I know I've seen these before, but I don't remember how to do it right now. So this, let me just distribute it. I want to play with this for a second. People like get the impression that everything's like a straight shot to the answer, but that's not always true. If you multiply log times log, you could pull that back into the exponent. I would love to use the sum rule here, but I can't do it. Oh, what if I exponentiate right here? Okay, so I'll make like 10 to the power of this whole thing. I don't know if this is going to work out, but we'll see. 10 to the power of this whole thing. So this is like log base 10. If they don't write it, it's base 10. And then, so this will be 10 to the log of x plus log of x squared. It's log squared of x, I guess is a good way to write it, equals 100. So this cancels there. Then this is an exponent rule. So when you multiply two numbers with the same base, you add their exponents. So this is going the other direction. Does this right here make sense? How I did the left side to that? I'm going to keep going, but if you don't understand that, stop me in the chat because I can explain that a little further. So this becomes x, and then this would be times 10 to the log of x times log of x. And then is still equal to 100. Now, I'm going to use another exponent rule, which says that when you take a base raised to an exponent and you raise it to another exponent, you just multiply them together. So this is x times x raised to the log of x. And did I just like undo the whole thing? Let's see, does that get us any closer? So then this is same base. Oh yeah, I think I just undid the whole thing. That's 100. Okay, where does this now work out? Oh! I think I got it. So to the 0 equals 1. So 0 equals log 1. No, that doesn't work at all. Where's it equal? Turn to the 0 equals 1. Okay. So we can go, we'll go back from the beginning. Hopefully I didn't totally put you off to this. So this is x to the log of 10 plus log of x, and then that becomes, use the product rule, the sum to product rule. This becomes log of 10x equals 100. Okay, tell me that makes sense, because I think that does it. Okay, so then I think we just need to use the log of both sides, so log of x to the log 10x equals log of 100, which is 2. And then this is log of 10x times log of x. Here I use the power rule to bring that down. Equals 2. That should be 2. Then we can if we make this did I do the same thing? Oh. So now I can pull the 10 back out. Plus log. No, I don't want to do that. Dang, this is hard. It's the same problem. If that keeps fucking out. What if I exponentiate both sides? Let me try that. So we'll do 10 to the log 10x times log x equals 100. So this would be 10x raised to log x. I'm just missing a trick, you know? So x log x equals 10. Oh, there it is. Okay. Log x squared equals log 10. Okay, does that make sense right there? Let me know if you need something. Okay. Then this is log squared of x equals 1. Take the square root of both sides. And you get log of x equals plus or minus the square root of 1. Let's rock with that for now, and we may need to throw out a solution. And then we'll exponentiate, or here, I'll break this into 2. Equals root 1, which is 1, or minus root 1, which is negative 1. And right here you can see which one to throw out. No, these are both good. And then so we'll exponentiate both sides to the power of 10. And this will be x equals 10 to the negative 1, which is 1/10. Man, that was tough. Questions, complaints, comments, concerns, critiques, criticisms, call-outs. That was really hard. Is that reverb still happening on the audio too? Let me know if that's still happening. I'm just going to keep... Yeah, that one was really hard. And like, I don't want to give you the impression that there's like some method that always works to solve these problems. Sometimes it's just like terrible, and you just keep trying stuff until you figure it out, you know? And that's okay. Like, it's brain candy, you know? It's part of the fun to just struggle with a problem. One thing that I can totally... Okay. That's good. I had like 2 audio sources coming in. One thing that I can recommend, you know, like process-wise, is that if you hit a problem like that, that's just killing you, leave it. You know, leave it on your desk, come back to an hour, 2 hours, 3 hours later. I don't know if the way you're getting homework is like it's due the next day. That's kind of a bad situation. I just saw that. I don't know, man. Comment. And so like that's anytime you're like creeping up into the frustration, like fatigued part of your study, just stop. Even if you quit for 10 minutes and come back, it's gonna. Okay. Should I skip 4 or should I just rock it out real quick? Determine the series of transfer. Oh, when you said series, I thought you meant like series, like infinite series, which I was a little bit confused. The series of transformations. Okay. So let's say we have a function g of x, which is equal to the log base 10 of x. Yeah, let's just do it. So we would do g of 6. Let's say negative 6x. When we do that, this shrinks horizontally by a factor of 1/6, and it reflects across the y-axis. So this is a horizontal shrink 1/6 and reflection over y-axis. Oh, whoa! I feel like a freaking celebrity. I got my first spam bot in the chat. Let me reported. I got my first spam. That's wild. Here, I'm going to make you a moderator. Don't let the power go to your head, okay? Okay, so then we're going to add 3 inside there. So we're going to do g of 3 minus 6x. This is, so since it's... yeah, it's crazy. Since we're adding 3, 3 is positive, the constant term in there is positive, that's shifting us to the left 3. Okay, so left, shift, 3. And we can talk about how I memorize these. Then, so outside we're just going to do the order of operations, so remember 2 times g of 3 minus 6x. Good. I hope they like it. It's been going for a while, but nobody really... Just like, I would go on Reddit and find questions and answer them, and then sometimes the cousins will come. What's HSRV? So the outside the argument of the function we multiply by 2, that's a vertical stretch by a factor of 2. And then the last thing we need to do, my handwriting's getting sloppy, is add 5. This is a vertical shift. And here, once we get to this point, you can see I've rebuilt that original function. This is a good question. I'm not familiar with that method. I could Google it. Do you want me to try to give a rundown on that method? You can kind of see how if I come across something, I just Google it and try to figure it out real quick. But I'm sure I can teach us both at the same time if you want to talk about it. This to me is like, if you do this method that I did here, it shows me that you understand function notation at a very high level. Factor out. You cannot factor out 3 minus 6x unless what they mean is make this negative 6 times x plus, what would this be, 1/2? Or no, it would be minus 1/2. Minus 1/2. Unless he means this. Oh, and actually, that's true. You should factor this out because I made a mistake. This is a left shift by, this is a right shift by 1/2. I should have factored that out. Is this what you meant by a factor? Honestly, like, yeah. You should always do that. I'm just a bonehead. I don't know why I did that. If Mr. McClintock recommends something, I would do what Mr. McClintock says. Like, if I knew no other information other than Mr. McClintock says do this, do what he said, because he's knows how to like ace these tests for decades. Yes, yeah, that's because when you factor it out, you can clearly see the right shift. Okay, yeah. And then this last thing is a vertical or no, that's a, wait, vertical shift by 5. Yeah, good catch on that factor thing. Yeah, always factor it. Is that what HSRV stands for, or is? What does that stand for? I'm just going to Google it. Okay. Horizontal translation, stretching, shrinking, reflection. Oh, that's interesting. Vertical translations. I would like to see HSRV for periodic functions. I don't think it works for periodic functions. I don't think that's... I think you can do it without this. This will absolutely work for quadratics, which is what this example thing that I found gives. It will... Yeah, HSRV is just like a procedure that they gave an acronym. It's horizontal translations, that's what H is. Stretching / shrinking, both horizontal and vertical at the same time. Which, if actually this is the order that I did it in, then reflections, X and Y axis, and they give it at the same time. I don't think that it matters, but yeah. And then vertical translations. That's the exact same order that I did it in. So let me give you my rationale for why I do it the way I do it. I'm going to zoom out, not that much. So the most important thing that we don't want to forget is to do this factorization. But then let's look at the general case. Okay, so suppose we have a function a times g of, here I'm going to use Greek letters. We're going to use alpha times f of beta times x, and let's go minus here so that this doesn't confuse us, and then we'll do minus gamma over beta, and that's everything inside the argument of the function, that's it, plus delta. Okay, so alpha, beta, gamma, and delta, these are all constant numbers. Okay, these are all constant numbers. We just don't want to say what they are. So the first thing that you got to recognize is that inside the argument of the function, inside the parentheses, this only affects the horizontal, the abscissa. Okay? That only affects the horizontal part of the graph. And it does it also opposite from what you would think it would do. So let's talk about this beta coefficient here. Beta. If beta is greater than 1, and I'm multiplying this by x, this actually will shrink horizontally. So multiplying by a number bigger than 1 shrinks. And I'm going to say the absolute, let's say the absolute value of beta is greater than 1. We'll get to that in a second. If the absolute value of beta is less than 1 and greater than 0, well, let's just say it can't be negative, so we'll just say less than 1. This is like multiplying by a fraction. So if I multiply it by 1/2, inside the argument of the function, it does the opposite of what you think it does. It stretches horizontally. So inside the argument of the function affects the horizontal direction, and it does the opposite of what you would think it do. So multiplying by numbers bigger than 1 actually does shrink. Multiplying by numbers less than 1 actually does a stretch. And when I'm saying greater than less than 1, I'm talking about absolute values. So now let's talk about if beta is negative. If beta is negative, it does a reflection. Over which axis? Well, the one that affects the x direction, the y-axis. So if I reflect over the y-axis, I'm affecting the x direction, which is what anything inside the argument of the function does. Is all of that clear so far about beta? I'm just going to keep going as if it is. Now, the next thing is this quantity here. If you subtract a number inside there, if that whole quantity, like you're subtracting it, whatever, it becomes a right shift. You would think subtract means shift to the left, but inside the argument it works opposite of what you would think. Okay, so when we're subtracting, like, suppose that this whole quantity is positive. So overall, the entire thing is subtraction, it goes to the right. Then the same thing, same kind of considerations outside. So let's look at the multiplication. This does the same thing. Multiplication is either a stretch or shrink. If the absolute value of alpha is greater than 1, it does what you would think. It stretches it. It's a stretching factor. If the absolute value of alpha is less than 1, meaning it's a fraction, okay, it shrinks vertically. Okay, so outside affects the vertical direction, and it works the way you would think it does. Multiplying by a number, absolute value greater than stretches, multiplying by an absolute value less than 1 shrinks. So those are your fractions between 0 and 1. If it's negative, it reflects in the way that affects the vertical. It reflects over the x-axis. That's such a trick question. If alpha, if I have negative 1 there, what axis am I reflecting over? The x-axis, because that's the one that affects the height. If beta is negative, it's negative 1, what axis do I reflect over? The y-axis, because that's what affects the horizontal. Okay? And then you could probably guess what delta does. If you add a positive number, it shifts up. If you subtract, it shifts down. Super easy. Give me a continue sign in the chat there whenever that's all like super painfully obvious to you. And then if you understand that junk, you don't need this like HSRV. Those things are for people who think that they can't figure it out on their own and they need these methods. Mr. McClintock is a master at getting everyone to get a high performing grade on those state exams. I still have nightmares about that man. Okay. Simplify the following. Okay, so now we are working on number 5. And I know I'm taking kind of a long time, so if you need less explanation on anything, let me know. That last bit on problem 4 on the transformations is actually kind of like important how I think about it. Simplify. So one thing about simplify is the definition is often really bad from algebra onward. Simplify means do all of the operations that you can do, and a lot of times that just becomes like it means everything that the teacher thinks it means, which is a little annoying. All right, so let's work on a log base 5 of 125. There's a couple of different ways you can do it. My favorite way is to express the number 125 as a power of 5, because that's probably what's going on here. And 5 times 5 is 25, times another 5 is 125. So this is actually 5 cubed. Then you can use the power rule to make this. And we'll just put parentheses since it's a function everywhere. And then these, since it's the same base as this, cancels out. So this is like saying, what should I raise 5 to get 5? And the answer is 1. So this is 3 times 1, which is 1. Or, sorry, 3. Okay, so that's A. And if you don't need this whole problem, just let me know. Okay, so same sort of thing here. You could do the exact same way and simplify this that way first, or you can use the fact that this is the same base as this log and they cancel each other out. They're inverse functions. And what you just get is 144 here. Yeah. I think that's fully simplified. And what is this, 12 times 12? I think, yeah. Be 120 plus 24 is 140, yeah. I don't know which version of this they want. This is probably the answer here. So that's probably what they want. Okay, C. Yeah. Okay, should I skip this whole thing? Give me like a yes, no, maybe so. Yeah, okay, we'll skip that. If anybody like comes in and asks for it, did you send this to your friends? Like, you don't have to send it to them now, but if you know anybody that's having a hard time, like, you might as well hook them up. Screen. Okay, we're going to 6. Do C. Gotcha. Okay, so I'm going to just write this by hand, save time. Okay, so C is 9 to the log base 3 of 20. So this is, you're looking for anything to do with the power of 3, and 9 is 3 squared. Log base 3. This is old homework, but I will tell a few about it because, word. Yeah, I mostly just am like looking for ways to volunteer as a tutor. Word. So then, this is like, so 9 is 3 squared, then you have an exponent rule that says when you have a base raised to a power and you raise that whole thing to a power, you multiply the exponents. So this becomes 3 times 2, or 3 to the 2 log base 3 of 20. And then this comes up to the exponent using the log exponent rule. And this is 3 to the log base 3 of 20 squared. And then these guys cancel since they're the same base. And you get 20 squared, which is 400. I don't think we need help. 6. Okay, skip 6. What about 7? Yeah, what we should really do is we should get you some like algebra and geometry students so that you can do that for a winter job, like an hour a night, and work like 5-10 hours a week during the winter, and you can just like work from your bedroom. Because that will level your math up more than anything else that you're going to do. Okay, so A. So this is 3 to the A equals 69. And that means 3 to the A equals, this is 3 times 23. Yeah, 3 times 23. And then we can divide both sides here by 3. And we get 3 to the A over 3 equals 23. Oh wait, are we solving for A? What do we do? Oh, I'm just making all kinds of stuff up. So, sorry, 3 to the A equals 69. And then let's take log base 3 of both sides. And then, so these will cancel and you'll just get A. And that's the answer. Yeah. Yeah, that's the answer. This is a number. I can estimate this. What would it be? It so we add 5 to both sides. And then we take the natural log, because the natural log has base e. Take the natural log of both sides. And so we get x minus 1 equals log of 10. And then we add 1 to both sides. And we get natural log of 10 plus 1. And this is a number. We can estimate that as well. Log 10 plus 1. Oops. When you put these on the calculator, make sure you are very careful with your parentheses. If you don't put this parenthesis there, and then you just like, it's implied that it's here. So again, this is the exact value, this is an approximation. If you write both, you can't be wrong. So now we got C, 9 to the n plus 1, or n plus 10. Plus 3 equals 81, so I figure this would be something to do with powers of 3. And so 9 is 3 squared. And so we can make this 3 to the 2 times n plus 10. Plus 3 equals 81. We can subtract 3 from both sides and distribute this 2 if we want. Yeah, why not? Equals 78. And then we'll do the log base 3 of both sides. And subtract 20 and divide by 2. And then I would probably even change this a little bit. Actually, maybe not. Yeah, I think that's fine. Maybe you put it like this. You could use a exponent rule here to make this a square root. I don't know if that makes it simpler. Let's estimate those. D 6e to the 5x plus 6. Oh my goodness, this is wild. Time out. There we go. So we add 4 to both sides. We divide both sides by 6, which is, what is that? 8 times 6 is 48. Yeah, that'd be 10, 9. And then we take natural log on both sides. Because natural log has the base e. Then we subtract 6 divided by 5. And, you know, you could, again, you could like, I'll write this. I wouldn't necessarily do this, but you could make this 1/5 log 9 minus 6 over 5, and then do an exponent thing here. But I don't see any good reason to do that, so this is simple enough. They may probably want an approximation, which is annoying anyway, so let's get them one. Log 9 minus 6 divided by 5 is negative 0.7606. So then we got e. Log base 8 of x squared minus 1 minus log base 8 of 3 equals 1. We can use a sum product rule here, so I guess it'd be a quotient. So this is log base 8 product, or the quotient difference here, right? So log base 8, this is going to become 3 times x, no, it's going to become x squared minus 1 over 3 equals 1. We could raise 8, like exponentiate it, so put both sides in the exponent of 8. So this cancels, you get x squared minus 1 over 3 equals 8 to the 1, which is just 8. Multiply both sides by 3. Add 1 and take the square root, and we should be careful to make sure that both of these provide real solutions. So negative 5 squared minus 1 is 6. Oh, no, that's 25. Okay. Rather, 25 minus 1 is, yeah, we should be, okay, 25 minus 1 is 24, which is, yep, this is good. Is that right? 24 divided by 3 is 8. And log of 8 is 1. Yeah, that's right. Okay. So both of these are good solutions. F log of 3x minus 1 plus log of 4 equals log of 15. Yeah. So let's subtract log 4 from both sides. Equals log of 15 minus log of 4. I'll use the difference to quotient rule there. And then we'll raise, each side will be the power of e, so it's like e to the log of whatever, so those cancel. And it'll cancel over here as well. Then we're going to add 1 and divide by 3. So 15 over 4 plus 1 is plus 4 over 4. And so 3x equals 19 over 4. And then we'll multiply, or divide both sides by 3. 12. 19 is prime, so this is reduced. And let's check does that work. 19 over 12 times 3 is 19 over 4, minus 1 is 15 over 4, times 4 is 15, so log of 15 is log of 15, so we're good. Okay, questions about that one? I'll just keep this here, and then if you bring a question, then I'll definitely go back to it. But I think you're slightly behind because you're pausing and stuff. That tool that lets me do that is called the transformation tool. Okay, cool. Yeah, I feel like a lot of that is just tricks that you get comfortable with over time. Like you see, I have a couple of essentially like rules that I'm going for. If I can package using the sum and difference rules, package things into the same log function, then I can raise it to whatever base it is, and that cancels the log function out. So that's like a really big strategy. And then the power rule is really important. Basically, just having some fluency with your power rules, or with your log rules, is the way to go. Okay. So if log of 12 is approximately 1.1, and log of 7 is approximately 0.8, and log of 8 is approximately 0.9. Fine, okay, so if we have log of 1 over 49, this is the same as log of 1 minus log of 49. And 10 to the what number equals 1? That's 0. So log of 1 is 0. 0 minus log of 7 squared, which is negative 2 log 7 by the power rule. And they say log 7 is 0.8, so this is negative 2 times 0.8, which is negative 1.6, ish, approximately. Yeah, sorry for moving around on you a lot. This should be right here. I want to make this to an approximation. Yeah, that's kind of a cool problem. This is something that you'll do later on in math quite often, is these approximations using, various methods. Sometimes it's not possible to know what something is equal to exactly with the techniques that we have available to us, so we need to use these like different forms of approximations, which is cool. It's neat that we have that available to us. Okay. Which one do you want to do next? Do you want to do 9, 10, 11? Determinative. Okay, yeah, this definition of continuous is really important. What have they given you? What's your notion of continuous? Because you haven't learned what a limit is yet, have you? Yeah, this is kind of a terrible question if you don't have a limit. Oh, you have heard limits. Okay, so do you want to skip 9? Okay. Determine the values of x that make the inequality. Okay, so let's go for 10. Yeah, 9's not bad. It's especially like it's straight from the definition. That's something that you're as confident in it now as you can be, and you'll get a more accurate definition of a limit at some point. Okay, yeah, let's skip that one. Do you want me to start the other? Did you email me the other one? You did. Series, but okay. If you still got gas left, I can do the next one too. How are you feeling, by the way? Okay. Yeah, I pulled it up. I'll start working on it. Boom, boom. Okay. Yeah. The notation is really weird. So let's see if we can figure out the pattern for these. A big thing is just like factor everything. So we've got -4, -8, -16, -32, -64, dot, dot, dot. So this to me is like -1 times 4, which is -1 times 2 squared. Okay. Oh, dang. So you guys have been sick for... What was today? Oh, whoa. Yeah, that's a bummer. Yeah, it's Saturday. Okay, so you're on the downswing. Well, hopefully you can get back to like feeling 100% soon. Yeah, I don't think I've had it. So this is -1 times 8, which is -1 times 2 cubed, and you'll start to see the pattern here. 16, -1 times 2 to the 4th. Okay, that's cool. So if we assign these like an n, so let's say this is n, our strategy is try to like write a thing so that we can, you could just figure out the next 3 terms. So I'm going to show you on this like trivial problem how to do this for real. So this is n equals 0, 1, 2, 3, 4, dot, dot, dot. We could index it by 1. It kind of depends on what kind of series you need, which is not really going to come up in this course, but we'll index it by 0. This is not a series. This is a sequence. So we have, let's call our sequence A. The nth term is going to be, so let's index it by 1 then, since it's a series. There's a sequence. So this is 1, 2, 3, 4, 5. So you're going to go -1 times 2, we want this to be times 2, it to be, start off with 2, so it'd be like 1 plus n. So if you plug in 1, it's going to be 2. If you plug in 2, it'll be 3. Okay. So basically, compare this number to n. And you can see it's always 1 more than that. And so that's how you notice your pattern if you want to set an index. So if you want to generate the nth term, you plug the same number in here, and then you'll always get the correct number. So we need 6, 7, 8. So we'll need A6, A7, and A8. So this is -1 times 2 to the 7, -1 times 2 to the 8, -1 times 2 to the 9. And you'll get more and more comfortable with this as you do these. But it just keeps getting power. So this is -128. And we could have went directly. If we notice the pattern, we just keep doubling. You could have done that directly. This is 256. Have you ever seen these numbers before? Have you ever noticed these anywhere? Like 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024. Yeah. What are these always associated with? You always see these when you're purchasing a certain type of thing. Okay. The place that this comes up is when you are buying like stuff to do with computers. Like if you look at how many gigabytes your cell phone has, it's probably 64 or 128, maybe 32. The reason why this happens is because they're powers of 2, and binary only has 2 digits. If we look at the set of binary numbers, it's just these are the only digits in the binary system. So let's say our normal base system is base 10. And base 10 means we only have 10 digits. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is a very natural choice because the first place probably everybody counted on was their fingers, and we have 10 digits. Go figure. That we call those digits. But if you wanted to express a number like, I don't know, 9, 8, 7, actually that's too many digits. Let's do 1, 2, 3, 4. So 1,234. This is the same as 1,000 plus 200 plus 30 plus 4, which is the same as 1 times 1,000 plus 2 times 100 plus 3 times 10 plus 4 times 1, which is the same as 1 times 10 to the third plus 2 times 10 squared plus 3 times 10 to the first plus 4 times 10 to the 0. Actually, you could get decimals like if you did 0.5. This would be 5. This would be 5 tenths. Our base 10 system is literally 10 as the base, and everything's a multiple of a power of 10, right? Well, to express these numbers in a base 2 system, you have the same thing, but those are arbitrary bases. Okay, that's why they come up. If you really want to push the envelope of what an arbitrary base means, you might have seen something like this. This is a polynomial. Polynomials are base x, which means the base can change. That's why we can add, subtract, multiply, and divide them, as you learned in Algebra 2. Okay, 10th term of the sequence. So this one is recursive. You'll see that whatever term n is determined by n minus 1th term. So there's no fun way to do this. We just have to start off with like, so we have A1, let's find A2, A3, A4, A5, A6. So this is given. And then this is A sub 2 minus 1 plus 2, which is a sub 1 plus 2, and that subs into here. Okay. So the idea, and you'll notice the pattern very quickly, is that we add 2 to each term. And so same thing, a sub 3 minus 1 plus 2 equals a sub 2 plus 2, and this is a sub 2. So we can substitute. So I'm not going to keep doing that process. What you'll notice is you add 2 to the number before it. That's what this says. So this is -4, -2, 0, and this is 4. So a sub 8 is, oh, they want the 10th. Yeah. They want the 10th. Say sub 9 equals 6, a sub 10 equals 8. There's, there may be a faster way to do that. Like you can do it with multiplication once you see the pattern. Okay, number 3. Boom, boom. Expand. There we go. Then determine if the following series is convergent. What convergence tests do you have? While you're thinking of that, I'm going to try to write this out. So it looks like each one of these has a factor of 1/5. So there's every term gets multiplied by 1/5. And then, okay, yeah, this is kind of surprising that they're talking about convergence. I guess you can do it with just a limit definition. So basically everything's going to be ratio test, and I always look these up. These come up in Calc 2 again. So let's say this is, I don't know, n equals 0 to infinity, and then this would be times n plus 1. Actually, let's blend index this. I want to make this blend indexed because it'll make it a lot simpler. Times n. Okay. So if you use the ratio test, you take the limit as n approaches infinity of the n plus 1th term. So you do 1 over 5 times n plus 1. That's how you generate the n plus 1th term, divided by the term before it. And the idea is like you're trying to see if going one more term adds very much to the total sum. So you take a ratio of a very, like, term way, like the infinitieth term, and then you do one more term after that. And if you see if that ratio is like, the ratio of those things is like big or not, okay? So the 1/5 cancels, so this is the limit as n approaches infinity of n plus 1 over n. Now we can use limit laws to figure this out, but let's like really think about it. Well, here, let's do long division. So if we do long division on this, like we do n into n plus 1. 1 times n gives us n. You subtract, you get 0 plus 1. What would I multiply n by to get 1? Well, it would be 1 over n here. So n plus 1 over n is equal to n times 1 plus 1 over n. This is just true. If you distribute that, you'll get it back. This is a trick. There's no reason you should know this. So 1 plus 1 over n. And then this is a limit that you know, and you can use the sum rule, and the limit of 1 is 1. So this is actually equal to 1. because that is 0. If you have a cake and you have infinity friends at your birthday party and you cut infinity slices out of your cake, each person's cake is approximately 0. That's how you interpret that. Okay, so the limit is 1 now. I think this means that the ratio test is inconclusive, so we need to look up the ratio test convergence. Ratio test. Boom, boom, boom. Yeah, it's indeterminate. Let me see if I can. What other tests do we have? Ratio test for sequence test. Test. Can't do that. Comparison test. I don't know any. I suck at the comparison test. Alternating. It's not alternating. Let's go there. Let's go there. Ratio test. Root test. Okay, so at a quick glance, does it look like the series terms don't converge to 0 on in the limit? Yeah, I don't see why it would. Test if a quick glance suggests that the series terms may not converge to 0 in the limit. Okay, let's try the divergence test. Divergence test. Okay. The limit doesn't exist, so we can't use divergence. Okay, can we go? Nope, can't use the absolute. Can we do? Let's try. I mean, I know this is divergent, but you have to be able to justify it. So let's say So here's the root test. L equals the limit as n approaches infinity of the square root of n of the nth term of the series. So you take the nth root of the nth term, which is the same as the limit as n approaches infinity of, and this is just a different way of writing it, over n. These two things are equal. And then let me know if you have any confusion on that. So this is very similar to the ratio test. If L is less than 1, it's absolutely convergent and thus convergent. If L is greater than 1, it's divergent. If L is equal to 1, then we have inconclusive, which is super annoying, because that's what happened to us here. So our nth term is n. So the limit, L equals the limit as n approaches infinity of the absolute value of 1/5 n raised to the 1 over n. And then this is the same thing. So this is always positive, since n is always greater than 0. So that means this is the same as 1/5 n to the 1/nth. And then we'll use a power rule here. And then this portion is equal to 1. So we just need to figure out what this does. So how would we word that? The nth root of 1/5. So this is going to be so this goes to 0. Oh man, this is really hard. Okay. Let me, Emma, did they give you a list of convergence tests? Or like, at some point did they discuss convergence tests with you? Because this diverges. This does diverge. Like if you keep adding to it, a bigger and bigger number to it each time, it just keeps getting bigger and bigger and bigger. And the reason I know this for sure is because if the sum from n to infinity of 1/5 n, this is equal to 1/5 sum from n equals 1 to infinity of n. The reason why is because of the distributive property, and this thing diverges. It's just like you keep adding bigger and bigger and bigger numbers. Yeah. And I really wish that I could figure out a way to show that. Anyway, this diverges. Here we go. This is like my least favorite part of Calc 2. These are powers of 5, so this is like so that's this. Let me know if you're comfortable with that. Yeah, there's ratio, root. There's a bunch. Here, let me actually show you the list of them. is... That whole website is amazing. This comes from Calc 2. So some things you're not going to be able to do. Like you can't do the integral test. You just can't do it. You can't use... Like on the last one, we got to indeterminate form, and I wanted to be able to use L'Hopital's rule, and I couldn't use it because you don't know it. What else? So ratio root, absolute convergence, or rather, comparison test. Maybe the linear comparison test would work. No, because we still need to... Oh! No, see this. No, we could not use the limit for that. Well, maybe I could think of a different one. We need something that converges. Well, I think this one we can just use the ratio test, so that's fine. Okay, so let's use the ratio test again. So we'll do limit as n approaches infinity of 1 over 5n plus 1 over 1 over 5n, and then this is equal to limit as n approaches infinity. We multiply by the reciprocal, and we get 5n over 5n plus 1. We cancel the 5n's. 5 to the n, we get the limit as n approaches infinity. This is 1 over 5. Right? Yeah. Which is 1/5. So this is less than 1, which means it converges. Then D, we have 1 plus 1 over 32 plus 1 over 243 plus 1 over 1024 plus 1 over 3, 5. So that's 1, 2, 3, 4, 5. So this is a power of 5. It's 5 to the 5th. This is 4 to the 4th, which is 2 to the 8th. This is 3 cubed. No, that's not right. That's like 7 cubed. 7 times 7 is 49 times 7 is 28 plus 63. Yeah, this is 7 cubed. Huh, that's weird. Okay, let me check to make sure that's... Oh, that's probably not right. So this is... So this is 5 to the 5th, I think. 2, 3, 4, 5, yep. And then... What is this, maybe? Okay, this is 4 to the 5th. This is probably 3 to the 5th. I think that's the power of 7. No, that's power of 3. Yep. 2 to the 5th? Okay. And this is 1 to the 5th. Alright, it's powers of 5. Or it's like something to the 5th. Okay, so this is the sum from n equals 1 to infinity of 1 over n to the 5th. So we can use the ratio test. This would be 1 over n plus 1 to the 5th divided by 1 over n to the 5th, which is equal to n to the 5th over n plus 1 to the 5th. And this is equal to 0, which is less than 1, so this converges. Is this equal to 0? No. Okay, this is equal to 1. Which is not what we want. Yeah, probably like he gave you everything you need to know in order to solve it, but you still have to figure it out, you know? It'd be no fun if you knew everything. You know what I mean? This would be 1 over n to the 5th. 1 to infinity. What's on? Sucks. Did you learn the P series, the power series? Yeah. Is there an option for these things to be?
I think you're supposed to run the test that you know, and you're supposed to say inconclusive, inconclusive, inconclusive. So you can say it's inconclusive. Okay. That's really important for me to know. Okay, give me 1 second. I gotta do the bathroom. Okay. So, I'm back. Oh, that was my... living life on YouTube. Was the audio coming through? Love it. Love it. You're supposed to be the moderator. You're using curse words in the chat? Oh my god. Worst moderator in the chat room currently. Pin. You're gonna get me kicked off YouTube. Or maybe by our powers combined. Okay, let me unpin that. Remove. I'm pretty sure the first thing I said whenever I made you moderator. Yeah, that's true. When I made you moderator was said, "Don't let the power go to your head." Man, that's crazy. I should have turned the gain down on my actual sound card, but whatever. Okay. So, all right. I'm gonna ask you this, and because this makes a huge difference how we answer these questions. Did you learn anything other than the ratio test? Do you have your notes that says what tests you know? Because I'm sure you don't have a book. All right, love face. Oh my gosh. This is relentless. This is insane. Thank you. All right, there you go. Best moderator ever. I love it. I love it. Yeah, I feel so great. I think this means I've arrived now. Okay, so you don't know which test you have. Okay, this is what I'm going to do. I'm going to read off. Man, how do I block this person? Put a user in timeout. I almost clicked add moderator again. Hide user. Bye, Felicia. Okay, series and sequence. Okay, I'm going to say some names of convergence tests. And you tell me if you know the test. Integral test, obviously not. Yeah, the buku bots. Do you know the comparison test? Or I guess that's what we've been. No, we've been doing. Comparison test, limit comparison test. You probably know that one. Alternating series, that doesn't really apply to any of the ones we've done. Absolute convergence. Oh no, that's a definition, that's not a test. Ratio test, that's what we've been doing. Root test, we tried to do that once. We got a, what's it called?
Inconclusive. Okay. Dang. Yeah, you don't know any of these. You know alternate. Yeah, we can use alternating series on number E, I think. Yes to ratio. So you know alternating and ratio. That's basically it, right? And you probably know absolute or comparison test, but I can't think of any other series that I like. I don't have like a compendium of series that I know that converge. Okay. So let's do the ratio again and just like this is not convergent. Let me turn the light on. So. Yeah, we get on E. Yeah. All right. So what did we have? We had like 1/5 sum from n equals 1 to infinity of n, and we did the ratio test, and so we did the limit of as n approaches infinity of n plus 1 over n, which is equal to the limit as n approaches infinity of 1 plus 1 over n, which is equal to 1 plus the limit as n approaches infinity of 1 over n, which is equal to 1. I don't know. I actually, if you only know alternating series and root and ratio, and then probably the comparison test, then I think that might be the case. Do you P series also? Okay, that does help. Partial sum series. Yeah, so P series will work for B, definitely. No. Yes, P series will work for B. P is greater than 1. I think we can use it for B. Okay, let's put a pin in 1, because actually that might be interesting too. Oh, we can use a comparison with. Okay, so let's do B first. So this is the sum from n equals, let's say, 0 to infinity of 1 over 5 to the n plus 1. No, I don't want to do it that way. I'm going to do the sum n equals 1 to infinity of 1 over 5 to the n. And then I'm going to do what's called disgorge a term, which is a really disgusting but official math word. So I disgorged the n equals 1th term. N equals 1 term. So now this is 1 over 5 to the n still. And then I'm going to re-index this thing. So here the first term of this would be 1 over 5 squared. So I'm going to re-index this thing. Plus the sum. Now it's going to be from n equals 1 to infinity of 1 over 5 to the n plus 1. So now we can test the convergence of this series. If this series converges, then this converges. Okay? And I think we have all of the conditions met. Okay, so when p equals 1, the power series is the harmonic series, which we... Oh, p is a constant power. No, we don't have the right thing. This is not the right thing. This is 5 to the n. This is not power series. So this is harmonic, so we know it diverges. We can't use power series for this. Let me see what else we got. Because it should be n to the p. Yeah. Are there any power series? Yeah, okay, D is power series. This is P series. This is harmonic. I still don't know what this is. This is going to be alternating. Okay. Oh. I think we can just use ratio for this. Am I being dumb? Oh, I'm being so dumb. B is ratio. Okay, I think I know how to do it all. I'm pretty sure this is ratio. Why did that not work? This is 1 over 5 to the n, which means we need 1 over 5 to the n plus 1 over 5 to the n, which means it's 1/5, which is less than, yeah, this converges. Okay, I think I got them all. So let's start with one, and then we'll just do them all like correctly. So harmonic. Let me paste this for you to see. I guess it's good that I need to review this stuff. Boom, boom, boom. T. Stretch. Enter. Okay. So the standard harmonic series is 1 over n. Diverges 2. Boom. And this is not even the harmonic. That's not right. This is harmonic. Is it? No, because that's 1 over 5 to the n. Geometric. Oh, maybe we can make... Oh. No. Term test. Those series that converge, those terms approach 0. Okay. I think this is called the divergence test, what I'm about to do. So... you take some n equals 1 to infinity of 1/5 n equals 1/5 sum n equals 1 to infinity n. So you do limit as n approaches infinity of n equals the limit as n approaches infinity of n minus n minus 1. Oh, it's the partial sums. Okay, yeah. We just do limit as n approaches infinity of n equals infinity. So this is diverges by divergence test. Okay,
So basically, if you look at the nth term of the series, if that does not go to 0, then the thing diverges. The nth term has to, the limit of the nth term has to be 0, otherwise the sum diverges. And when I'm saying the nth term, I'm saying in the sequence, which the sum of which is the series. If you look at the nth term, which for us is n, if that does not converge to 0, the limit doesn't go to 0, then the sum, the series diverges. That's called the divergence test. Okay, B. So here we have the sum n equals 1 to infinity of 1 over 5 to the n. Can we use ratio? Yeah. So we'll take the limit as n approaches infinity of 1 over 5 to the n plus 1 over 1 over 5 to the n, which is equal to 5 to the n over 5 to the n plus 1. And then this gives us 1/5, which is less than 1, so it converges by ratio test. Okay, so B is good. Then this is a power series for sure. So this is D. Oh, we skipped C. We didn't even look at C. C is alternating? Or ratio? So C, sum from n equals 1 to infinity of negative 1 over m. So we'll do limit as n approaches infinity of negative 1 over m plus 1 over negative 1 over m equals m over m plus 1. And let me check something real quick. So So this thing here is itself. I don't know why I'm writing M. Oh, because they gave us M. Okay, so this is one minus 1 over M I don't know if that helped. We can use comparison test for this. So we need to show that this converges. So I disgorged a term, and then now I have it indexed starting at 2. And what I'm going to say is that 1 over m is less than 1 over the natural log of m for... Oh no, that's not true. Yes, that is true. Okay. So let me, if you're still with me, if you look at the graph of a linear function x and the log of x. Log of x grows slower, right? So n is always greater than log, or I guess we're using m. M is always greater than the log of m. And so if I divide both sides, so since this number is bigger, that means the denominator is bigger here. And that means that this quantity has the smaller number in the denominator, meaning it's bigger. So this is true. And that's true for all m in this series. So if I show that this converges, then I show that this converges by the comparison test. No, that doesn't work, because that doesn't converge. Man, this is tough. I actually think this diverges anyway. I'm going to show that over n diverges. Oh! Is it p-series? It's p-series. I think it's p-series. Yeah. This is divergent by the p-series. Because p is equal to 1. P equals 1. D. God, that's annoying. Is this also p-series? This is n raised to the 3. No, to the 5. 2 to the 5th is that. 3 to the 5th, 4 to the 5th, 5 to the 5th. Okay. So D is all positive. 1 over n to the 5th, n equals 1 to infinity. Convergent by p-series. P equals 5. And E should be alternating. Let's hope. Let's see if I can figure it out. So this is powers of 2 on the denominator, and it's alternating. So it's like 1 minus 1/2 plus 1/4 minus 1/8. So this is the sum from n equals, let's say, 0 to infinity. And this is -1, some power of -1 times 1 over 2 to the n. So 2 to the 0 is 1, so this first term is 1. We want this to be positive, so let's make it raised to the n. So n to the 0 is 1, so this all becomes 1. N to the 1, this would be negative. Yeah. Okay, so this is our series. And it's alternating. Okay, suppose that we have a series of the form the sum of some nth term in a sequence. And either it's -1 to the power of n times some other term b to the n. That's what we have. Or -1 to n plus 1 times b to the n, where b is positive. The b term is positive for greater than or equal to 0, I should say, for all n, so non-negative. Then if the limit of the b term, the bth term, approaches 0, and this is a decreasing sequence. So this is exactly what we have. This is that. Let me change the color. So this is that. Come on. Here we go. And then this is that. So we do have the correct form, and then the b term needs to be non-negative for all values of n. And this can never be negative. So the exponent won't make it negative. So we're good. We have both of those conditions. Now we need the limit of the b term to go to 0, which it does. The limit as n approaches infinity of 1 over 2 to the n is equal to 0. Then we need this to also be decreasing. So as n approaches infinity, 1 over 2 to the n decreases. And I don't know that you have a way to show that something is decreasing with pre-calculus techniques, but you could just say this. So now we have those two things, so converges by alternating series test. Oh my gosh. And I think you have disappeared by now, so I'm just going to tell you the time when I... Is that the last one? Thank baby Jesus. Okay. What time are we? 2 hours and 14 minutes in. Okay, let me text you because I don't think you're there anymore. Oh, you're here. Okay. Yeah, sorry. I know how annoying it is to watch me work these out. I'm particularly bad at series. Okay, so get rid of all that crap. I mean, I'd rather be helping you with some spoiled rich kids. I think you understand it just fine. It's just like knowing which test to use is kind of a... It's something that you develop intuition for over time, and I just don't do that many of these kinds of problems, so I don't have it. And if you stick around with math, like you'll come across this again in Calc 2, you know. Okay, what do you think we're going to use here? Yeah, memorizing the test. Yep. Can you guess on this problem which test we'll use? I hate memorizing. I just don't want to do it ever. Coffee. Yeah, so you do understand it. It is alternating. So, basically, we need to show like a n equals -3. Which is Nope, this is not alternating. This is not alternating. Yeah, it's not alternating. Because it's not to a power. The negative factor is not to a power. This is the same thing as -3 times the sum n equals 0 to infinity of 2 over 5 to the n. So I think we could use ratio here. So we need to show that this converges. Because the negative times 3 times that will converge. So let's do 2 over 5 to the n plus 1 over 2 over 5 to the n. And then this is the limit as n approaches infinity, which is equal to 2 over 5, which is less than 1. Ratio test. Yeah. Oh, you got it. Nice job. Yeah, crushing it. When in doubt, use the ratio test. That's what I remember from this stuff. And I would love to do more, like, upper level math classes, but then after calculus, there are very, very few people study anymore, and most of them don't need tutoring. My favorite thing about working with you is, like, you need zero algebra help whatsoever. So I can just go as fast as I can write, and you're like, okay, got it. Determine a power series representation of f of x, and determine the interval of convergence. How do you know how to do power series representations? This is so stupid. Why are they asking you this in pre-calc? This is ridiculous. I don't understand how you could possibly know this. Good work. Yeah. Well, yeah, I don't know why they're covering this in a pre-calculus class. It shouldn't be in pre-calculus. This is like Calc 2 stuff. Especially this. Okay. Let's see. Oh, maybe. What if we say? Just. This is ridiculous. Okay. What's your teacher's name? Yeah, this is what I thought it was going to be. I'm watching a YouTube video on it right now. I've never heard of him. Have you seen this thing yet? Right. It's essentially a geometric series, right? So think about what's the common ratio. It's actually like x. So first it would be if you choose n equals 0, this is x to the 0, which is 1. So then multiply that by x, multiply that by x, multiply that by x. So it's geometric series. So how can we do this? There's got to be a way to like make this pop out. Ignore this stuff up here. That's nonsense. So I think the plan is we're going to try to like manipulate this in some way. And so I'm going to change x. I'm going to do a change of variables because we're going to need that. I'm just going to make this y. It's not like xy plane, but yeah, we're going to make it y so that we can just change our variables. Let me see how he does this. All right. So what if we multiply this by 2 over 2? So I'm going to multiply this by 1. I'm going to represent 1 as 2 over 2. So this becomes... No, that's not good. I know this is... Oh, there it is. Okay, this is all algebra tricks. So this is the same as 1 over 2 times 1 minus 3 halves x, which is the same as 1 half times 1 over 1 minus 3 halves x. And then if you know that 1 over 1 minus y equals the sum from n equals, I think, is it 1 or 0? I can look real quick. 0. X to the n, where the absolute value of x is less than 1. Oh, and this should be y. I'm doing a change of variable. Y. Okay, so if you know this form, then we can focus in on that bit right there. So what I'm going to do is I'm going to say let y equal 3/2 x, and then we can do 1 over 1 minus 3/2 x equals the sum from n equals 0 to infinity of 3/2 x to the n, where the absolute value of 3/2 x is less than 1, and then to get the rest of it, we'll just multiply that 1/2 back in. So we get 1/2 times 1 over 1 minus 3/2 x equals 1/2 times the sum from n equals 0 to infinity, and this is going to be 3 over 2 to the n times x to the n, and so let's look at this absolute value expression. That means like -1 is less than 3/2 x, which is less than 1. If you, that portion going from here to here, I want you to like take a second and convince yourself that that is what the absolute value means. Because it is true, and no amount of explanation is gonna like convince you of that. If you just really think about what absolute value means, you will get that, and I think that's like a whole separate discussion, so take that for granted for this moment. Now I'm going to multiply these together to get back to the original thing, so it's like 1 over 2 minus 3x equals, and then we can bring this in using the distributive property. N equals 0 to infinity. This is going to be 3 to the n over 2 to the n plus 1. So I'm just multiplying that 1/2 by that. So essentially using a power rule there. So x to the n. And the interval of convergence is between negative. Okay, so we're going to multiply by 2/3 here. And this should be good. That should be everything. Let me look back at what they said is the problem. Determine a power series representation of f of x and determine interval of convergence. So this is the interval of convergence. Yuck! I should probably like commit that to memory, but I refuse. I don't know why I would ever want to do that. This is a gross homework. What do you think about number 7? What unit is it? Just like the one right after Christmas? Okay. Yeah. It's a point discontinuity there for 7. And behavior is going to go towards y equals 3. yeah, fitting an exponential is pretty easy. Yeah, I mean, it's those tests. You really have to. After we talked about the like series or the sequences, it's pretty easy to like if you list out the sequences. Rather, if you list out the sequence, like write a bunch of terms out, and then say what n should go there, it's pretty easy to figure out what's happening. Like, figure out, is there a power of something? Do I have a negative coming in here? Probably have the power of a -1, maybe. You know, that you can work through those. I think you really are having convergence issues, which is what everyone has. And I still have problems with that. I should probably just do like a million. I did the entire Calc 2 book on OpenStax. Like, I did every problem in the Calc 2 book, and I still just can't remember the convergence tests. Be careful not to drop a root in number 10. It's a classic rookie mistake. I do it all the time. Yeah, fitting exponential is easy. Yeah, you're crushing it. Thanks for being the best moderator to ever moderate a live stream. Ooh, we got so many playbacks. I don't know how my live stat. Here, let me show you what the live stats say right now. Import animation frames. Yeah, let them, you know, I'll do your guys' homework. I can't get in trouble for cheating. It says the average watch time is 37 minutes 58 seconds when it's very clear that you've been watching it for 2 hours. So I don't know how that's possible. All right, sweetheart, let me know if you have any other questions or anything. And yeah, you're welcome. I like helping you. Yeah, send me all your homeworks. All right, feel better. I'm gonna go eat some food. You're very welcome. Anytime. All right, bye YouTube.